Okay, Mr. Luang, FRQ number 2. Well, first off, mass is 5, first 5 seconds, and then we have question A, draw a straight line that represents the data. Data is going to be time in the x direction, 0, 1, 2, 3, 4, and 5. It's going to be time. And then we have the Fn, or the forces, which is going to be 0 down here to 100 up here, 80, 60. It's going to go by an interval of 20. And straight line represents the data. Well, at 0 seconds, it's going to be at 100. At 1 second, it's going to be at 80. 2 is 60. 3 is 40. 4 is 20. And 5 is 0. So then, best straight line is just going to be, it's just going to be a straight line right here. And yeah, label this force. FT, forces. This one's gonna be T for time. Yeah, that's the graph. It's gonna be a force versus time graph. And then for question B, or for part B, using the information to derive an f of t function, well, we know that the force starts at 100, so the equation is going to be f of t is equal to 100. It's going to be a linear line, so we can use the y equals mx plus b format. The 100 is going to be at b because that's the y-intercept, and then it's going to be, the slope is down, it's going to be rise over run, which is down 20 over 1. So it's going to be negative 20t for time, because it's f of t. We replace x with t for time. And that's going to be the f of t function. And that's part B. For part C, we derive an acceleration function. Well, we know the equation is going to be net force is equal to ma. And since the mass is 5, no, it's 5a. And since the net force is given here, we're going to say that you divide 5 to both sides, and that's going to be your acceleration. So we can just take all of these intervals and divide it by 5. And we could just divide this whole equation by 5, right, to get a. So f of t over 5 is equal to 100 minus 20t divided all over 5. And we'll get f of t, or we can replace f of t with the a, since we know that f of t is net force. So then this is net force divided by 5, which is equal to a. So we have a is equal to this equation, and we can simplify it straight away. 100 divided by 5, that's going to be 20. 20 divided by 5, that's going to be 4t. and that's going to be the acceleration function, a of t. For D, we're going to have acceleration versus time graph, so a of t, and then we have t, which is acceleration versus time graph. And we're going to be able to graph the acceleration and time graph. It's going to look similar. It's going to be a linear line because F and A are about the same, like linearly. Yeah, it's like, yeah, it has a linear relationship. That's what it is. So we can just graph it. Maximum point here, it's going to be at 20. Since that's the y-intercept, and it's going to decrease from there. So we can just do the times first, because it's on the same interval. And we can just subtract by an interval of 4 every single time. So it'll be 16, 12, 8, 4, and so on. And it'll be a straight line. Down across. So that's going to be the acceleration graph. For E, what information can be extracted from this? Well, we could, since we know the equation, well, but it says from the graph, right? So assuming we don't have the equation, we can still find the equation, of course. But we can take the area under the curve to know the velocity, since area of the curve is, or area of the line is the integral, and the integral of A is velocity. So we can find velocity from 0 to 5 there. And we can just integrate the whole equation to get the acceleration. We can integrate the acceleration to get velocity, and we can integrate velocity to get position. And yeah, that's the information you can get from that. Moving on, have part F. Derive instantaneous velocity. As I said before, we can just use the equation that we have right there to integrate that. We're gonna get 20t, because we're gonna add a t minus the it's gonna become a square, so the t is gonna get a square, and it's gonna be 2. So you divide it by 2, it's gonna be 2t squared. And yeah, that's gonna be the velocity function. Well, there's a plus c too, but we can assume that c is 0 in this case, because it's the first 5 seconds of motion, so there's probably not any motion before that, right? And if there's no motion, that means velocity is 0. So just ignore that c. Part G, what information can... So we can just take the area under the curve to determine this, as I said before. So we can do the delta x. So this is for part F. We're moving on to part G. Just gonna take the delta x right here, multiplied by the height of the whole thing, just 20. And then you divide that by 2 to get the area of the triangle, because base times height is the area of the rectangle, and divide that by 2 to find the triangle. And these 2's are going to cancel out, so it will be equal to 5 times 10, which is just 50 meters per second. Well, positive, of course, because it's moving in the right direction. And we just take that as positive. And then for h, using the derived function instead, we can just plug it in at 5. So h, we're going to do 20 times 5 minus 2 5 squared. 5 squared is going to be about 20, which is 25. 5 times 5 is 25, times 2 is 50, be 100, since 20 times 5 is 100. It's 50, so we get 50 meters per second. Of course, positive, just again traveling in the positive direction. Part I, derive an expression for the function of time, or position time. We just integrate the velocity function to get well, we bring it up, so it's gonna be t squared, and it's gonna be 10 because we divided by 2, minus 2t to the power of 3 over 3, plus c for the initial position, but we can assume the initial position is 0 because it does not give us any information on where the initial position is, so we can assume that's 0. So don't really need that. And yeah, that's I. So now we have to graph it. To graph, we're gonna have the time, of course, which is t, and we're gonna have the x of t, which is the position, and yeah, so we're gonna do 100, or since the time, we just do the times first. 5 4 3 2 1 0. And when we plug this position function into the calculator, we're gonna get about, we're gonna plug it in, graph that. It's gonna be like this, and then we can just trace it after it's done loading. 0, it's gonna be 8, or 0 0 1, so on and so on, right? And max, it's gonna be 500 over 3, so we'll do that as our top. And then since it's divided into 5 parts, we'll just do each go down by 100. We erase this part right here to get a little more room. It's 400 over 3. 300 over 3 is going to just be 100. 200 over 3. And 100 over 3. So now we can just graph the graph. This similar graph, so it's 1, maybe 28. So we can just say it's about here is 25. So we'll just go a little bit above that. And it's gonna be curved, so that. And we're gonna do at point 2. It's gonna be 100, a little over 100, so we be somewhere right here. At point 3, it's gonna be 72. And we know, and since 72, we want to put it into threes. 216 over 3, right? So let's go back to the graph. 216 over 3, be a little above here. Not quite at the 20. And then we're gonna have the point at 4. We have trace 4. It's gonna be 350, which is gonna be, since this is 300, it'll be about halfway through. And we're gonna have at 0.5, which is 500, so we just do it right here. Yeah, that's gonna be the graph. We have sub things here. Draw the instantaneous velocity. I'll use blue for that. At point 2, it'll be like this. Be a tangent line down here with a slope of that. And then average speed from 0 to 1. So you take the point 0, 1. Graph that. Just a straight line. And then from 0 to 2, use a black pen. Be a little bit higher. Slope will be a little bit bigger. Switch back to red. 0 to 3. 3 right here. Switch black to black. 0 to 4. So about there. And again, these slope are slowly increasing, right? Because smaller slope, bigger slope. So the average is probably increasing little by little. From 0 to 5 next. It's gonna be from here to here. So we just use that red to show that. And yeah, explain what happens at that. It's gonna increase because the well, as I said before, the average is slowly increasing, and since the velocity, the average velocity function is gonna be delta x over t. Since delta x is definitely increasing, and t is increasing by a smaller number, well, of course it's gonna increase, right? It just makes sense. Okay. Okay, now calculate the average velocity between 1 and 3. Well, average velocity says delta x or delta over t, delta t basically. So from 1 to 3, we can set up the equation. It's going to be 3 minus 1 for the time. And delta x is going to be the x at, or the position at the point of 3 minus the position at 1. And that's going to be equals to the average velocity. The average from 1 to 3. Right? And that's going to be something over 2, right? And if we plug those into our calculator, and since we already have the position graph, just gonna do trace 1, 3 minus trace 1 divided by 2, and change that into decimal. Get easier. Divided by that equals 94 over 3, right? And which is about 31.33 meters per second in the positive direction, because of course it's going on the right. It's going rightwards, right? Okay, that's it. Number 2 done.